Hey, yo, what's up? Saturday morning, March. No, it's not March. It's April 3rd. Man, oh, that desire to stay in March and to hold on to the time that's passed has uh, ever increased in me as I see the winter fade away into the niceties of spring. No, just kidding. It's cold as heck in winter around here. Um, this Saturday morning, I'm going to be working on another problem. It's not my typical tree or, uh, I guess, non-tree problem. I wanted to try something with some arithmetic and arrays, and just try to see if I can throw something quick together. So another Leetcode easy problem, um, and this one is called maximum product of two elements in an array. By the way, if you like my content, like this video, subscribe, comment, hit the links below, and yeah, just keep engaged with my videos if you want to see more. I'm glad to put out more interesting tidbits on how to get better at algorithms and, you know, find more optimal than brute force solutions to existing problems and further the understanding of elementary CS. Okay, so without further ado, let's go on with the question. Uh, and by the way, this question is kind of liked. Um, about little more than 1/4 of people seem to like it. Okay, I have to still look into what that means. Whatever, what are people's dissents versus praises of problems? But anyway, given the array of integers nums, you will choose two different indices I and j of that array. Return the maximum value nums I minus 1 times num j minus 1. An example is if you have an array 2, 3, 5, 2, you return 12. If you choose the indices 1 and 2, you will get the maximum value that is nums of 1 minus 1, nums of 2 minus 1, and multiply those two together and you get 12. Okay, the same thing. Similarly, you choose an index I and j and you multiply them together and you get 16. Okay, so and so on and so forth. With two numbers, you get 12. Okay, so this is probably one of the most straightforward worded questions that you could see, but it's also an interesting question because the brute force solution can be coded up pretty easily, right? Let's do that right now. So we have a max value j equals I less than nums dot length I plus. Okay. And we have another inner loop here, so that's the outer loop, and we're going to loop through the inner and outer loop. And we simply multiply. So remember, we have to do this if I not equal to j, because if we're looking for two different indices, right? Max equals max. Then we do nums I minus 1 times nums j minus 1. Don't forget the parentheses. And max. And we return max. Okay, so and you can see, oops, this should be j. Don't forget your indices during an interview. You may actually get dinged for that. And then if you submit that, then obviously sleep very slow. Okay, faster than 5.49 only, and a very weighty space consumptively. The space I don't really take that seriously, honestly, but the speed is the important one here. Well, the space is important, but the space is inaccurate, I think, in Leetcode. But so why was this so slow? Obviously, we're doing O of n squared work. As the asymptotic upper bound, and this is actually, which is also actually the average work as well here, right? Because we're always going through every element in the array, right? So it's not only that it's upper bounded, but it's also average bounded. So what do we do to improve this? So we have to start going into our data structure lore. Now there's a number of ways to make this faster. I'm going to go into a mid-tiered way to make this faster. And that would be of using one of my favorite data structures, a priority queue. So I will call that a heap. And we want to be clear, min heap, right? I'll explain in a minute why I'm doing this. And I'm giving it a capacity of 3. I only want it to store 3 elements, okay? So what am I going to do here, right? So we're still going to iterate through the array. I equals 0. Nums.length. I plus plus. Now here's where the meat of the logic is, okay? So if pq.size is less than 3, pq.add, I'm calling my priority queue min heap. I always default to pq, but you should name variables qualitatively. Min heap.add nums of I, else min heap.pull, min heap.add nums of I. Okay, that looks weird. What is this? What's going on here? Well, let me get through the whole thing because it gets a tiny bit more weirder, but I'll explain in a second. But if you're good with algorithms, you can already pick it out, you know what's happening here. So now if pq.size equals 2, I'm going to explain all this in a second. Return pq.poll minus 1 times pq.poll minus 1 should be min heap. I always do that. Min heap, and min heap, and then otherwise min heap dot poll, okay, and return the same thing. So I'm just going to copy this here, make it a little quicker. Okay, so let's try running that. Did I spell it wrong? I must have spelled it wrong somewhere. That was in line 18. Min heap. Okay. That's accepted. And run it. Oh, slow. But okay, see the time. It depends, right? Like, but it's faster than. It's a different solution. It's a little faster than the other solution, but the key is in asymptotic time it's faster. Okay, so and what is going on here? All right, let's talk about it. This min heap is a data structure that automatically sorts items as they get put into the heap. Okay, so I'm adding a heap. I'm adding a number every single time to the heap, and it's automatically sorting in a factor of like log n time the items from smallest to largest. Okay, I gave it a capacity of 3 because I want to have 3 numbers in here that I'm always doing a comparison against: the smallest, the second smallest, and the largest. Okay. So basically, this is my quick, like more neat way of keeping track of the second smallest element and the second largest element and the largest element. Okay, and basically what I'm saying is that if anything, if I have 3 elements in here already, I'm going to this is going to be organized from smallest to second largest, smallest so far to second largest so far to largest so far. I want the next element that comes in, I want to get rid of the smallest and now compete that element against the two remaining elements, which are the second largest so far and the largest so far. And once I compete those will reorganize again into a new third, second, and first. Okay. So basically, what that's going to do is that's just, you know, pretty much always going to maintain. There's not much thinking to do at that point, because all I have to do at the end, if I have only two elements, then I'm going to just, according to the original condition, just subtract one from each and multiply them together, because that's obviously going to be the max product. And then if I have three elements or more, all I need to do, I only have three elements in my priority queue. So I'm going to get rid of the top element, and then the second highest and the highest found in totality over the entire array will filter to the top, right? And I'll just multiply those together, because that will have to, by necessity, be my result, because we've already done the work of organizing these through the loop. So what is the runtime here? So the outer loop gives me O of n, right? O of n, right? And then the inner loop, so you might think, oh, well, it's log n, right? No, it's actually log 3, right? Because I'm going to, or 3 log 3 at worst, right? Because I'm organizing this priority queue in constant time. So the constant factor is 3 log 3. And then that basically boils down to O of n work, right? So the reason why it's probably a little slow is because the constant factor is high. We can do a little bit. We don't necessarily need the priority queue to find the second largest and the largest element. We can probably just maintain a reference to them in an array structure and just like resort them. But I found this a little more nice and a little more artistic, I guess, in writing this algorithm. So yeah. Decided to go this way, and I'm sure you can find a faster solution. Well, anyway, yeah, so that's it for today. Like, subscribe, and do all that good stuff, and we'll see you guys tomorrow.